Hey robot makers, do you want to learn how to build your own custom machine learning model that can do object detection using Python and PyTorch? Then this is the show for you. So let's dive straight in. My name is Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Cool, let's get over to our keynote and make a bit of a start. So why is C3PO or C2PIO saying YOLO? Anybody got any idea what that's all about? We'll get into that in a second. So the process of building your own machine learning model, I'd say it's pretty straightforward. There's a number of different steps that we need to go through. Some are more simpler than others. So the very first one is to collect a whole bunch of images. So what I want to do today, I want to build a machine learning model that can detect different types of microcontrollers. So I've got a couple of microcontrollers here, for example, with the Raspberry Pi Pico 2 there. We also have a BBC microbit there as well. So what I want to be able to do is take a whole bunch of pictures, lots of different angles, lots of different lighting scenarios, different surfaces from different angles, as I've said. The more the better. We need at least 100 images per each object that we want to detect. So that's kind of what I'm aiming for. I've also got a ESP32 camera there as well that I'm going to include in the model. So I did spend most of Saturday taking lots of pictures and then doing the next step, which is labeling the images. I'll show you how to do that in a couple of seconds time when we get into the demo. It's quite a fun thing to do. It does get a little bit laborious after a while, but that's how we actually build up the assets that we're going to use to train our model. The next step then is to split those images that you've labeled and you've taken. You're going to split the folder that's got all that information in into two parts. You're going to create two folders. We're going to create a train set and we're going to create a test set. So the train set is what we use, the data set. All those images are going to go into the model to be trained on, and it will never see the ones that are in the test set. They're going to be used to make sure that our model is working properly, and we can evaluate it against that to see how well it can detect an object on an image it's never seen before. Once we've done that training of the model, we can then evaluate it. There's lots of different stats and graphs and things that PyTorch, which we'll be using today, gives us to evaluate this. And you can see where there's particular models might need a few more pictures taken, some different scenes that you might want to put them in to get the graphs to be where you want them to be. Then we'll deploy the model. And what I was hoping to do today was I was hoping to deploy one of the models onto the new Raspberry Pi AI camera. I've got set up next to me, and it turned out to be a lot harder than I expected. In fact, I wasn't actually able to get this running, and there's a number of reasons why. We'll get to that towards the end of the show, but I'm hoping to follow this up with another video where I'll show you how to compress, quantize and load this onto the Raspberry Pi AI camera. But we can use the model that we created today. I'll give you a demo of that and we can see how well that goes. So the first thing we need to do, here's a bunch of BBC microbits that are on my desk, and you can see there I've taken them from lots of different angles, lots of different camera, focal lengths, things like that, different lighting conditions. These ones have all got the same background on the same desk, so I need to take them and put them in different places to supplement that and make the model even better. So the more that you can take, the better. You need at least aim for 100 images of each object. Use different cameras, different focal lengths, different lighting conditions. I found when I was testing this in low light, it didn't really work very well, so I'll need to take some more samples in lower light. And different focal lengths, different cameras will also give you a better model as well. And we're not looking for like 4K images either. We're actually going to squash these images down to quite a small size. And the actual colour isn't that important either. It's more to do with just the objects and the detail that makes up that object for us to capture that. And don't forget, if you're taking a picture of loads of BBC microbits, for example, you might want to flip it around and take pictures of that side, maybe edge on, maybe some extreme kind of angles. The more angles you've got, the better, the more able the camera, the model that we're building will be able to detect this in any scene that it comes across. So that's collecting our images, that's a load of fun. The next bit, which is annotation, labeling the images, we can use some software like Label Image. This is available through pip. You can do pip install label image and it will install this particular software. We'll have a look at this, like I said, in a minute or two. And we're going to label the objects, and you simply do that by clicking and dragging a rectangle. I think you press W to make it into rectangle mode. You draw a rectangle around the object. They're not all nice and square on either, so sometimes you have to draw a rectangle quite, the bounds are quite outside of where you would think it to be because it's kind of at an angle, but that's what we need to do. And then a little pop-up window will appear and we can then name the object. There's a list of things that we can name the object from. We can have as many of these as we like. I think the mobile SSD model has over 1,000 different classifications, so we can certainly have at it with all the different microcontrollers we want to train this on. You can see there it comes kind of preloaded with a couple of examples: dog, person, cat, TV, car, meatballs, marinara sauce. Completely random. I also get added to the end of that, and it's quite intelligent. This, if you like press a key, it'll auto complete what it thinks that could be and drop down if there's multiple options for that. So you get into kind of a flow with this, and you can have multiple images, multiple objects in one image, and you can draw as many rectangles as you like around them and have them labeled individually. It's quite clever in that it can do that. So what it will then do is it will, when you click save, it will save either as a Pascal format, or it will save as a YOLO format, and I think there's another one. We want the YOLO, you only look once format. That will create a text file, a .txt file with the same name as the image that you've loaded in, and in there it will have a couple of things. It will have a number, and that's a number from that list you can see on the right hand side there. That's the class number, so it doesn't have the class name itself, just like a number representing that. And then it'll have an X, Y, and a width and a height as well, but they're expressed in a sort of normalized way, so they're a value between 0 and 1, and that's because if you bring in a really large, I'm making my arms large here, if you bring in like a really large image, you want it to be able to scale that bounding box wherever it is. So depends on the size of the image. This doesn't care about that because it's normalizing that height and width. Just give that a second to catch up. So we just had a bit of a second there where the stream was catching up with me. Okay, so next up then we have splitting the images. So we have a special function that we can use in PyTorch for actually splitting the image set, and in that image set is essentially a folder with images in it and the labels for each one of those images. We can split them into the training and the test, and we can do that in a kind of proportion, like 80-20 ratio. So 80% for the training, 20% for the test, because we want as much as we can to go in that training model, but we also want to keep some back that it's never seen before to show how well the model is actually working. So once we've done the splitting of the images, then it's time to get in to train the model itself. So this is the funnest bit and the bit that takes the longest time to do, depending on what kind of hardware you've got. So we're going to be using a library in Python that's called PyTorch. I think this is a Google or Meta created one. I can't remember who created that, but it's one of the big companies anyway that have created this. And we're also going to use Jupyter Notebook. This is really good for working with different data sets, and you can essentially rewind and play back different steps of your code, which is really cool. So if you're testing things out, things don't quite work the way you expect, you can just update the code, run it again. It'll carry on as if it's run the entire code up to that point, which is really neat. We'll have a look at that as well on the demo. So to install Jupyter Lab, you simply do pip install Jupyter Lab and then just type Jupyter Lab correctly. I think I've got a typo there on my slide to launch that. Now the training itself can take a couple of hours to do. I ran 50 epochs, 50 cycles of training, and that took an hour on my Mac M1, which is Apple Silicon. And I was also using the Apple Silicon MPS, which is like the accelerator that's built into Apple's. If you did that just on the pure CPU, I think it would take a bit longer. If you've got like an NVIDIA, you can also use that as well. So there's different options for speeding this up a little bit, but it will take a while to do. Once we have the model built, we can then look at a couple of graphs. You can see there that confidence curve. You can see there's a couple that it's not very confident about. So the the Arduino Nano Every, I only took a couple of pictures of that, so it's not very sure about that one. Whereas the ones that I've got the most on there, the Microbit, it really is confident it can detect those. And then there's a couple of other graphs there, and you can also see on the right hand side where it's detected various different things. It's put a little bounding box around it, and it's given it a label as well. So that's it detecting these things based on the training. And then once we've done that, we can deploy the model. So we end up with a file that we can copy and paste onto other devices. We can share that with other people, and these are quite small, about 30-40 meg when I created this one. They can be even smaller once we quantize and compress them, and we'll get into what that looks like in a minute or two. So, in fact, here we are now. So, compressing and quantizing. So, compressing is where we will look through our model, and our model is like a tree, it has lots of different branches on it, each representing a different feature of the machine learning model. And sometimes we can squeeze these two together, we can fuse them together, and essentially they become one layer rather than 2 or 3 different layers. It's an operation that we have to have the computer do itself. I don't think you'll be able to do this manually. And in doing that, you can make the model smaller, quicker to process, but you can also lose some of the quality, the granularity of your model. So it depends what you're going for there. Quantizing is where we take the actual values that are stored in the model. The model is essentially just a whole bunch of weights, and these weights are stored as 32-bit floating point numbers, so they're very large numbers. And what we want to do is squash them down into an 8-bit number. So if you think about your microcontrollers, if I pick up this microcontroller here, for example, this has got a 32-bit processor on it. If I grab the Arduino Uno clone that I've got here, this is an 8-bit processor. So this is like, 4 times more capable from a processing perspective than this Arduino Nano. And essentially what we want to do with our model is make it work on really small, less capable devices. So by making it 8-bit integers, that means that our model will be significantly smaller, and we can do that with this quantizing where we don't actually lose a lot of quality. It's surprising how well the model will work with that lack of granularity there. So that's the compressing, and here's the quantizing. So yeah, it reduces the precision of the model's weights, typically from this 32-bit floating point to 8-bit, reduces the size, the memory footprint, which is really important when we're looking at things like that AI camera, which has only got a couple of meg of onboard RAM. So it means that the model can fit entirely in the memory, and it also means that it runs more efficiently on hardware with limited resources. So you can run, I understand, some models on an Arduino Uno with this 8-bit processor. Not these particular machine learning models with cameras. I'm talking more about things like gesture recognition. So you could make something, if you shake it a particular way, it would recognize that as a gesture. It speeds up the inference. So when we're actually training our model, if we've compressed it down, the other way around, once we've deployed this model, if we quantize it, it will actually make it quicker to work. So yes, we're just looking at quantizing here. It'll speed up the inference on the device that's actually using the model as well, because there's less data to crunch through. So by having that low precision, faster operations, it means that we can operate that at more frames per second. So once the deep learning is applied to the we often apply this to deep learning models after they've been trained. So this is kind of like a final step, a final kind of spit and polish on that. We do need to make sure that the hardware is quantize aware, and this is where I came across issues with the Raspberry Pi official AI camera. So when I quantized the model, it didn't like the method of quantizing that had been performed. It said it wasn't compatible with the toolkit that we was using. So that was quite frustrating that happened. Anyway, so we'll have a look at that a little bit later on. And so this is particularly useful for deploying models in resource-constrained environments like Raspberry Pi, smartphones, and IoT devices as well. You can see that we go from this really nice, crisp 32-bit floating point all the way through to our 8-bit integer. Cool. Let's move on to our next one. So the AI camera itself then, I've actually got this installed right next to me. If I just go over to this camera here, this model I've got here has got 2 cameras in it, and one of these is, I think it's this one here, this one is the AI camera. So in theory we'll be able to use this once we've got our model all working. We'll be able to upload that to that camera and then detect things using that model there. If I've got time in a second, I'll show you that working. I'll show you both cameras working at the same time, which is quite a neat thing to do. We could get some stereo vision going on there, which could open up all kinds of interesting possibilities. So yeah, the Raspberry Pi AI camera, which they launched a couple of months back now, is based on the Sony IMX500 sensor. So this is a 12 megapixel sensor. and it can do onboard inference. So it can take a machine learning model like one we're going to build. Once it's been quantized to 8 bits, it can then be used directly on the camera, and it will do all the processing itself without having to use the CPU of the machine. And that means it's really, really quick. It can work on even the very first generation Raspberry Pis without any extra hardware, because it's all built into the camera. So how does this image processing work? So on a traditional kind of setup, we have the camera, which is just taking data from the sensor, and it's pushing that down into the computer that's running it, the device, and that does all the image signal processing on it. So it would run things like our PyTorch model. It would detect images, and it would then process that as an output. Now sometimes you can add an accelerometer onto the device. So Raspberry Pi have got the AI hat, and that means that it can do some of that post-processing once the images come from the camera. But these are all kind of extra costs, if you like. On the AI camera itself, on the IMX500, they've got this image signal processor built into the camera itself. It's got the AI accelerator within the camera itself, and when it takes the image data, it can then run it through that image signal processor, and as well as giving out the video stream, it can also output the tensor information as well. Just watching my stream there. Come on, come back. I think real issues with this. I think it's Restream.io. I think I might cancel my subscription to that and just broadcast directly to YouTube rather than all the other places. Sorry about that bit of a delay that we've got. Okay. So with the camera, there is an online toolkit that you can download. It's called the Sony Model Compression Toolkit, and the idea of this is you can download this into your environment, your PyTorch environment, and you can use it to compress the model, quantize the model, and then upload that to your Raspberry Pi camera. I found this really difficult to use, so on the Apple Mac that I'm using the processor on there, the GPU processor, do a lot of the model training, and then once we've outputted that, we can then use it on our model. And because I'm using the Apple's built-in capabilities, there's only a couple of types of model that we can use, the kind of algorithm in the background. So this QNN pack and FBGem are two different kind of algorithms for producing the internal machine learning model. And of course the one that's paired with the Apple, which is that QNN pack, doesn't seem to work nicely with the Sony Machine Compression Toolkit. So really frustrating when these things are kind of not working together nicely. I will get this working. It is just a matter of time before I've just cracked through that, and probably spoken to some people at Raspberry Pi as well. So what's this Jupyter Labs all about? Let's have a look at that, shall we? So Jupyter Labs is an environment for creating code. It's kind of an interactive environment, a bit like an IDE. But it has some extra features. We can do live coding, we can do visualizations, and we can also put text in there that's got all kind of markdown formatting within our notebook. It's really, really nice way of working. It's got this nice modular design. You can even have terminals in tabs, and your code side by side with the outputs in different panes. So it's a really nice environment, and the output is really rich. We can have these rich media outputs, so we can have within our notebook graphics, graphs, data that's coming from our code directly in one environment. So I really like Jupyter Notebooks. I find if I'm working with data, if I'm learning something new, this really helps me refine my code, because I don't have to run the entire program again. I can just break it into smaller chunks and just run one bit at a time. So really, really friendly. And you can either run this locally on your machine, or you can use something like Google Colab, which is just Jupyter Labs, but a free version that they host in the cloud. So if you like what I do and you're bearing with me through these interrupted streams, then please give this video a like. Drop me a comment, let me know if you've got any machine learning hardware or any models that you would like to build. And if you've not already subscribed to the channel, please consider subscribing. It means an awful lot to me. I do put a lot of effort into these videos most weekends and most evenings during the week to produce the content for them. And I do go live every single Sunday at 7 o'clock British summertime currently. I think we're just in the last couple of weeks of British summertime, and then we'll be back over to GMT, Greenwich Mean Time. So for this particular project, I also did another thing. I built a laser cut model for holding two Raspberry Pi cameras behind the eyes. and yes, works with the new Raspberry Pi AI camera as well as the existing camera modules as well. It's basically just 3 layers of 2mm basswood cut to this particular shape, and all the files are available at kevsrobots.com. You'll find there if you go over to C2PIO, you'll find the files that you're looking for. So it's like camera 2 Pis oh, because it's version 0, not based on any kind of popular science fiction thing. So yes, it's got 3 layers that combine the head. You can see it's got like the face plate, then it's got the front piece and then the back piece. We paint it all gold. Jenny did all the nice painting on this. The eyes are painted yellow, so you get that nice kind of effect there. And the interlocking stand pieces kind of have that kind of cross brace, I don't know what you call that, but it stands up really, really well. And you can see it's just stood up next to me on the desk just there. So it came out really, really well. If you look overhead, you can even see it's got a Raspberry Pi 5 with all the cameras plugged in as well. So pretty neat. So you can cut your own if you've got access to a laser cutter. So on the back there you can see we have the Raspberry Pi 5. The cameras are easy to remove, they're not sort of glued in or anything. It's really fun and really practical to hold the cameras in place while you're working on particular projects, and it's really quick to build as well. It didn't take very long to cut out these pieces, paint them and glue them, and have it all working and standing up. You can see there that the camera modules and the C2PIO's eyes perfectly aligned, so we get the iris of the eye and the camera lens perfectly aligned. So it doesn't need any glue, they just kind of friction and fit in the back, no problem. Okay, let's get over to a demo, shall we? This is a bit I've been looking forward to doing, so I'm just going to go over here. So this is Jupyter Labs, this is Jupyter Notebook, and the environment that we're working in here, you can see that we have a couple of different tabs on there. We've got these cells, as it calls them, these different pieces of code, or it can be code, it can be raw, it can be markdown. So at the very top here, if I just double click into this, that's markdown. That's a format for using text to represent really rich text. So that little hash, that little pound sign there, means that this is a heading 1 style. If I did 2 pound signs, if I do that, then that makes it a heading 2 style, so it's not quite as big. If I go for 3, then that'll be the 3rd style, and if I go back to 1 and press the run button, we're back to there. So we can have intermingle with our code, we can have really rich text. So I think this is a really nice feature of Jupyter Notebooks. Next cell that we have here has just got some code in it. So there you can see this is some Python code. I'm using the Python language there. So a equals 1, b equals 2, c equals a plus b, and then we say print c. And if I clear the output of that, we just clear that cell output, and then I run it, you'll see that the output of that cell appears below it, and we can clear out that as well. So it's a really nice way of working through one bit at a time. You can see how easy it is to install Jupyter Labs. You just do pip install Jupyter Labs, and then you'll have it installed in your environment. And it can also do diagrams. So this, if you've not come across Mermaid before, Mermaid is a really nice markdown based language for creating diagrams. You can do all kinds of flow charts, Gantt charts, state machine diagrams, all kinds of things. You can see there we've got this A, B, C and C, and we've got all the different B goes to C, C is a decision, it's in these curly braces, which makes it that kind of diamond shape. A has got like hard brackets on it, whereas the B has got the round ones. So when I run that, you'll see that there's hard versus round edges. We've got some text in the middle there, and we've got that decision with 1 and 2. It works out all the logic. We just type in what we want it to draw, it'll draw the rest. So you can do that in Visual Studio Code as well if you're interested. You simply just have to do 3 little backticks, Mermaid, and then 3 little backticks at the end. And anything in there that follows the Mermaid language, it will render OK. And you can see that I've got like another heading. If I pop out this here, you can even see that we've got like a structure like bookmarks with chapters and so on based on our heading levels. And that's just more marked down there. So that's Jupyter Notebook. It's a really nice environment. If I go to the file thing there, I can see all the different files that I've got in this environment. And you can download this as well. This is available in the show notes. This is go to github.com/kevinmcaleer/object_detection, and you'll be able to download this code yourself. So in there, I've got things like all the assets, all the different images, all the text files. If I open up that text file there, you can see that's a class 15 object, the X and Y, width and height. And if I click on that image as well, you can see that's the microbit. So that's how I've classified it. If I click on the classes.txt, this is all the labels, all the annotations that we've made using that tool. So speaking of that tool, let me just flick over to a terminal. Let's open up a new terminal, and let's just do let's go into Python. Let's go into object detection, and let me do. I'm just gonna load up the virtual environment. So just activate that. Right. So if I now do image, label image, I want it to open up like so. So this is the image label. I'm just going to open up the directory that we want to work in. So that's going to be the assets folder. Let's open that up, and let me see if this is going to work okay. I think it might crash. No, it's going okay there. Okay, so we can see there we've got all these different images, and how we'd use this software to create our labels. We press the W key. Oh, it has crashed. There is a bit of a bug in that software. I think it's best to use it by downloading the software rather than doing a pip install of image label. For some reason, it has got like a bug in it. You can actually update the code if you want to. All you need to do is find that line 530, and where it's got the instruction there, draw line, you basically just want to put an int over there rather than a float, and that fixes the image problem up. But anyway, that's how we get that software working. So I'm coming back over to Jupyter Notebooks, and I'm going to load up the test 2. Right, let's get to the very top of here. So this is, you can see that we've got some mermaid to explain how the diagram or the flow is going to work of our code. So we're going to collect some images. We've got some images, you can see there on the left hand side. I've annotated those. I spent a good afternoon going through drawing rectangles over all the different objects in each one of the pictures. It takes quite a while to do that. You can see I did that like 10 hours ago. Splitting the data, so we can do that in our code. I've written a little piece of code that can help split that apart into the training set and the testing set. Once we've done that splitting, we can then train our code. We can run the PyTorch stuff that will actually build the model for us. That takes a while, and we can then do the evaluation at the end, and I'll show you what the graphs and things look like for that. Once we've done that, we can deploy it. We can take the output of this, which is like a little PyTorch file, or we can even export this as an ONNX file, which is that Open Neural Network Exchange format. As a final step, we could also quantize it. We could reduce it down to like an 8-bit integer rather than the 32-bit floating point, and then deploy it to things like the Raspberry Pi. There's a bit of extra work to be done on that bit, and kind of that's as far as I got. I spent hours and hours trying to get that working, and unfortunately it didn't work. So let's have a look through the code on this notebook. So got a bunch of imports there. We need to do pip install PyTorch, which is the main library that we're using on here. And I've also got things like Pill, which is the pillow image manipulation library. Torch Vision is part of PyTorch as well. So the first thing we need to do is define 3 functions in our class, which is this YOLO dataset. So YOLO, if you remember, is you only look once. And this is a popular machine learning data model. We're going to take a data model that already exists and train on top of that. And that means that we don't have to learn from scratch. We're kind of enhancing the already existing model. This is a very popular way of doing just that. So I'm going to take the YOLO model and work with that. So the first thing we need to do is initialize a couple of things. So we need to set up an image folder, the label directory, and any transforms that we want to do. So a transform, if you think we get the images in and they come across as a great big image and they might have several objects within there, we draw some rectangles around it. Now for different types of machine learning model, we might want to actually have just the contents of those rectangles saved as separate images and have all those images the same size, so they have to be reduced or stretched in size. And we also might want to make them black and white. You can also make your model better by rotating these randomly and flipping them, doing all kinds of things like that to kind of generate more pseudo data from our existing data set. So transforms help us do all that kind of stuff. And then we want to have a list of images file names, so we can just do this list directory, image directory, which we've got there, and that'll give us the actual file names that we're working with. We want to filter out anything that isn't an image. So when I was creating these, they were .jpeg with an E in it. I actually ran this through Adobe Bridge to reduce them down a bit so that they're not stonking big 3 or 4 megabyte files. They're all quite small, under 100k hopefully. And you can see there we're basically just filtering out anything that doesn't end with PNG, JPEG or JPEG with an E, because I was getting this .dsstore, which is like is it .thumbnails on Windows, where you've got thumbs.db, which is like performs the same kind of function, just has a cache of file thumbnails and things in your file folders. So length is just going to return the length of the number of files that are in a particular folder. So that's what this underscore len does. And then this double underscore get item gets the next item ready for processing. So you can see there we're going to get the image file name. We're going to get the index from the list of files. So each file has got sequential numbers 0 to however many you've got. I think there's about 700 or 800 pictures in here. We've also got things like the path where we currently are, the label paths and the label file names, and the boxes are the rectangles that we're going to draw. The labels are the classes, the things that are in the boxes, and then we're simply going to go through each one of those files and open them up and add them to our library. So we're going to look at, when we looked at that text file, for example, if I go back to that one there, you can see it has a number, and then it's got an X and a Y and a width and a height. So if I go back over here, we're basically just taking that in, an X and a Y, width and a height. We're then going to convert it to this YOLO format, which is used with PyTorch. So because these are all numbers between 0 and 1, they're already in the right format for this YOLO processing. We're then going to append the boxes and the labels with what we've just gone through, and it's going to loop through that until it's gone through every file that's in that folder. Next, we want to convert these to tensors. We looked at tensors last week. If you think a single number is a scalar, 2 numbers would be a vector. If we have a number of vectors together, they would be a matrix. And if we have a number of matrices together, then they would be a tensor. So a tensor is kind of a mathematical structure for holding lots of information that's all kind of related. Kind of consider it to be like a spreadsheet with lots of different worksheets in it. Okay, we're going to set up the target directory, or dictionary, sorry. So the target is going to end up going to start out with nothing in it. We're going to then add to it the boxes and the labels. So target's going to have boxes and labels as 2 dictionaries within it. And then we're going to apply any transformations that we might want to at that point. And then we're simply going to return the image in the target, which has got all that information in it. So if we wanted to, we could run that and see what happens. I don't think it doesn't do anything interesting, but it has run because we've got a number in there. That's the current number, which increments each time you run a particular block of code. So next up, we're going to define any image transformations, resizing, normalization, and so on. Normalization typically means if you've got an image and you've got so many pixels in it and you want them all to be the same size, normalization can help us do that by making them all, the image sizes are essentially between 0 and 1, and all the pixels between that are kind of floating point numbers. So it's just a way of representing that. So we're going to resize our images to 416 by 416, and this is what YOLO uses. And then we're going to make that into a tensor, so it's going to be, the tensor will contain all the pixel data from that transformed image. And then we need this custom collate function. So this is just a way of grabbing together all the image labels and the images and sort of smashing them together in a single object. So that's what this block of code is doing there. So we can run that. It's not going to do anything particularly interesting there. The next piece of code I put in, because I was getting all kinds of weird things where it kept trying to download a custom tutorial kind of data set, and it's because it thought it was in users kev python rather than users kev python object detection, which is the folder I'm in. So this os.change directory basically makes sure that we're in the right place. It prints out that we are in the right place, and it gets the current working directory to confirm that. So the fact that they're both the same means that things are working good. Next up then, so associate the labels with images. So this is how we can do some of the, before we split the data, we just need to associate those two together. So we've got the image directory, the label directory, and we're going to create a data set. So that class that we created earlier on, that YOLO data set, it takes an image folder, a label folder, and any transforms. So our data set is going to be loaded in there. And then we want to take that data set and load it into our data loader. So data loader is a PyTorch structure. So that's going to take in our data set. It can do that in a number of batches, so it doesn't try and do everything at once. And this can help just balance the load. And if you've got a multiprocessor machine, it can help use that as well. Shuffling it means that we can shuffle the data set so that they're not all in the same top to bottom order. And again, that can help with the training process as well. And that collate function, we're going to pass that in too. Once we've done that, we can iterate through all the images and the targets in the data loader, and we can see what they look like. So the output here, you can see this is what a tensor looks like. It's just like an array of arrays. So we've got the boxes, the labels, boxes and labels, because we've got two sets, the test and the train. And you can also see within those what they actually look like. So this is the widths and the heights, the x and the y's of all those different graphics, that all those different objects that are inside our thing. So there's lots and lots of them. So that's that. So next up, we want to split the data sets into our test and train. So this splitter helper is a piece of code that I created, and essentially it just takes in an image directory, a label directory, an output directory, and what the ratio is between that split. So 0.8 is 80%, that it's going to be the training ratio. So that will create a new folder. If I go over here, you'll see we've got this split folder, we've got an images and a labels. This will actually create this for both the test and the train. So there's our training images, here's our valuation images, the test images, and similar with the labels that match up for each of those as well. So that's what that split dataset helper function will do. Right, we're getting closer and closer to the training now, promise. So what we need to do now then is load up those different training and the test data sets. That's what these two lines here do. I'm going to set up some batch sizes. So how many does it do at a time? How many could it do it simultaneously? So that we're not overloading the machine. And we're going to create the two data loaders, one for training data, one for testing data. And then we say for X and Y in the test loader, get the shape. This just shows us what the shape of those tensors are. So we can see we've got two different groups there, and then the X and the Y size, or the width and the height size, sorry. And then it's just going to do that for the first batch. That's what that break does. So it's just going to go through and just show us a couple of those just to make sure it looks correct. Right, and then we can use this Torch Vision utilities. You can see we've got some images embedded down here. Again, this is why I like Jupyter Labs. And this will help us visualize what's in our set, so in our image set. So if we bring in the NumPy is a Python number library, helps do lots of clever maths and stuff. So we usually call that NP for NumPy, and PIL is the Pillow image manipulation library. So I've got this little function here, visualize image grid, takes in some images, I've set it to be number of items per row 20, that seemed to be a good number, and we're going to show that these they're like 12 by 12 pixels high. That's what that fig size means. And plot is a function that we can use from it's either the Torch Vision or the PIL. I think it might be the PIL that does this. So yeah, image show, NumPy transpose. This is basically just how we get all the different data into our plot. We're going to turn off any kind of X and Y axis, and then we're going to show it. So that's what that output there is. And we simply just go through and say visualize this for all the images that are in the training data loader. So you can see there we've got a number of images. When I did this one, I didn't have all like 690 images that are in the folder there. I just did about 100 or so. Might have been about 70 or so. Okay, so that's what that function there does. That helps us see that the image data is coming in. It kind of looks correct. Next up, we've got some more imports. You can have each imports. Normally you would have them at the top of your Python code, but you can actually have them at any point during your code. It's just normal best practice to have them at the top. But when you're working in these notebooks, it's good to kind of chunk out your code and have them kind of independent from each other, even though they're cumulative when they run. So any functions, any variables that you define higher up, they apply further down as well. So you can see here we're going to bring in the tensor converter, so to PIL image. This will convert our images into tensors, or the other way around in fact. And you can see there, visualize the cropped boxes. So what this is going to end up with doing, if I scroll down, you can see that this is the cropped boxes that we're looking for. I'm not sure we actually need this one. I think this is me just trying to visualize what is in that data set. Okay, next up, this is where it gets interesting, depending on what kind of CPU you have. So you can either use your central processing unit, your graphics processing unit, or if you've got some kind of accelerator, such as the Apple MPS device, then we can use that. So we have got one on this M1 Mac that I'm using to broadcast today. This is Apple Silicon, and this is like, I think they call it Metal. That's the name of their accelerator, and it basically uses a special part of the CPU that has these neural network processors in it. So you get so many of them for each different thing. It's what's going to run all the Apple Intelligence when that comes out later this month. So if we've got CUDA available, we will use that. Otherwise, we'll just use the main CPU. So then we're going to define a neural network. So from Torch, import NN. So this is going to define our neural network. You've got these different layers in the neural network. So you can see there we've got a sequential layer, and this has got a linear, a ReLU, and another linear in there. And these numbers have been kind of provided as part of the PyTorch tutorial, so they're the ones to go for. So don't worry about what they are. This is just the neural network that we're building now. And this forward function, we also need one of those as well. This is going to just return some logits from that linear ReLU stack. So if we say model equals neural network to device, then our model is available. We have a neural network that's not been trained yet. So model is going to house our neural network model. So you can see there is output all that information. We can set up a loss function. So when we are building our model, you'll see this term loss used, and this is how we can see how accurate our model is. So we want as less loss as possible. We've got this optimizer as well. And again, this is just another way of making our model work more effectively. So you don't have to worry too much about that. Right, so we're going to define two functions now. One is the train function, and one of them is the test function. So this is if we want to do the manual training and testing ourselves. So we will look at the size of the data set from our data loader. That length function just gets us that. And model.train will put it into the training mode, as evaluation mode or training mode. And then for batch X and Y in the enumerate data loader, X to device, this will basically go through each block of data that we've got in there from our images. So you can see that it's just going to work through that. It's got these back propagation, loss backwards, optimizer step gradation, gradients. Don't worry about those too much. This is just kind of how it works. If batch 100% is, so that is a modulus of 0, then we can say that the loss value is greater than this 7f. I can't remember what that means actually. Anyway, and we have the test function. That one basically does the same kind of thing. And finally, we get to the training of the model. So let's have a look through this. So Torch backend MPS enable fallback true. So what this means is some features are not available for the Apple Silicon. So it's got these accelerators, but they don't do everything. And this is where I was talking about this mismatch between the tooling and what our hardware can do. So this line basically just tells Torch, if you can't do it on the Apple Silicon accelerator, then just use the CPU. That's what the fallback means. You can also set an environment variable to do the same thing. I've done both of them just to be sure. And we can say device equals MPS if Torch MPS is available, otherwise use CPU. This is where we use the pre-trained model, so you'll be able to download the YOLO version 5 model. You'll be able to download that and use this in your code. So YOLO version 5 su.pt, that stands for PyTorch. That's an existing model. It's not very large, and we're going to basically use that as the basis to put our training on top of. You don't want to build your model completely from scratch, because there's millions of images have been trained through this model, and because of that it's got all kinds of intelligence in that model that we haven't got if we built it from scratch. So without going into too much depth about that, it's best to use an existing model and build on top of that. So we're going to move the model to the MPS device. So that basically says to the to our hardware, use the MPS device, our accelerator, to do the machine learning. Now really you want about 50 to 100 epochs to do the training to get some accurate detection. I found that 50 takes about an hour using the MPS on the Mac Pro M1. I put it there as epoch 1 just in case I wanted to show you this, but it'll max out my my computer potentially if I do any more than that, but I can run 1 epoch. There's not a lot to see there. We can have a look at the output that's already run. I've saved that. So model.train, we then pass in the dataset.yaml file. This is what gets produced. Let me show you what that looks like. We have to produce this. So we say here is the training split data for the images. Here is the test set, the valuation set. We want to say the number of classes is 24. There was 24 different things that I've detected that I want to detect, and that's what they are. So it'll enumerate them 0, 1, 2, 3 and so on to match up our labels. So you can see there all the different things. I made the mistake of not actually cutting these out before, so if we want to detect a microbit, I think that's like number 15 in this list. Yeah, I wish I'd have done that before, because otherwise I have to go back and go through every single one of those labels and update it. I'll probably write a Python script to do that, but there we go. So that's what that dataset.yaml is. The epochs will be the number of epochs we provided. The image sizes 640 is the sizes we want to work with. The quantization aware training, this thing here is a Q&M pack. That will do some quantization, but not the right quantization to work on the AI camera, frustratingly. And then we say quantization prepare QAT, that's a type of quantization. There's about 3-4 different types that we can use for that. And in place just does it on the existing model rather than having a separate model created. If it's CPU, then we can cut out some of those things. So we can just say use the Q&N pack, prepare the quantization, and then do the quantization. So this is what the output of this training function looks like. So you see there it basically just gives you a load of config of how it's going to work. It then goes through all the different 24 classes, and it will tell you how many images it can detect for that, I think. Let's just go through there. So it's got 262 layers, 9 million parameters, 9 million gradients, and it's going to be 24 gigaflops to do this. It transferred 421 of 427 items for pre-trained weights, and what it will do for each run of this, for each epoch, it will create this runs folder. So you can see there, and under detect, you've got all these different runs. So every time you run another epoch, it creates another folder and adds to the model. So you can actually stop it midway through and come back to it, a bit later on and have it run again, and it'll just carry on where it left off. So you get these extra folders in here. So that's what's going on there. And you'll see these kind of salmon coloured bars pop up, and it'll say, well, for each epoch you've got, it'll run through it. It might take a couple of minutes for each one of those. So that one took 0.1 hours to do. So at the end of that particular epoch, running through all those, you can see there that we've got 22 images of the microbit, 4 of the ESP32 cam, 5 of the ESP266, which I later realised when I flipped it over was actually ESP32. Never mind, I can rerun this again. And we've got 1 of the Arduino R3, so it doesn't really know anything about that, and 1 each of these Raspberry Pi. So I've really not given it anywhere near enough images, so it's not going to be a very good model. But this was me just trying to learn the tooling of how all this works. So once we've done that, we can then quantize it by just ensuring we're in the training mode. We can then switch back over to the CPU if we want to do it that way, and then I can output. I can use a single image to test the results of that, and this metrics will give me some metrics similar to what we've got here as an output. We can also convert it to this ONNX, and this is an open neural network exchange format. So sometimes when you download a neural network model, it might be in this ONNX. You might see that often described around. So we can basically just do model equals a YOLO, and we're importing that from this Ultralix, which is one of the libraries that they write PyTorch essentially, and this will then output it as this ONNX format. So we're going to import what we've outputted. If I go to that model train 23, which is that folder there, you can see we've got a whole bunch of things in here, and this was the output of the model. When I finished the training, we had a 17 meg file. When we output it to ONNX, it doubles in size for whatever reason. So the PyTorch model is a lot smaller to use. Okay, so quantizing for this with the Raspberry Pi, this is where we need to make it go from these 32-bit numbers down to this 8-bit integer version. And what I found was this is the example of the code that we need to bring in. There's so many custom layers. We need to install this ONNX. And something called Hugging Face as well, which I thought was an interesting word. Is that from Aliens or something? And yeah, it basically crunches through all this, and the idea is it will output a quantized version of this for the Raspberry Pi camera. But what I found is it just fails. And it fails because it will say that the original model isn't quantized properly. If we try and quantize it with the built-in tools, it says that's the wrong type of quantization. And yeah, the tooling doesn't sort of pair together very well. So what I'm going to do next week is speak to somebody at Raspberry Pi and see if they can help me get a pair of things that actually work together well. So you can see here, this is how we do the quantization. We load in the model, we load in the checkpoint. The checkpoints are these different training folders, so you can actually go back one if the model's got worse. And you do need to evaluate them each time you come out with a when you've done more epochs. And that's where this best or last model will appear. So you can see best and last are currently the same because the model wasn't really trained enough yet. But sometimes you'll see that the best one is a previous one, it isn't the last one you've done. You cannot overtrain the model. Okay, so yeah, this is more of the how to export an ONNX format. So we're bringing our best quantized one, which is an output from the previous step. We've got some options in here on how to do that, and then what we end up with is this ONNX file again that doesn't work. It still doesn't work, and this is where you get into like the real nitty-gritty batch norms, ReLU layers. It gets really complicated very, very quickly. There you go, ReLU and SILUs. So yeah, that was kind of way over my head at that point. So this is what I like about Jupyter Labs. You might try a piece of code. If that doesn't work, you can just not run that next time. You can just step over. That one doesn't work either, so we can step over that. We can then go into one that might work. So I've got another one, which is the model int. If I jump back to the main folder, I think we can find that one. I thought that was going to be the one that would work, and then that didn't work either. So there we go, model int 8. So instead of being 17 or 34 meg, it's 8 meg, it's much smaller. And that would be about the right size to work on the Raspberry Pi AI camera. So that's why I like using this Jupyter Notebooks. Now we can actually test out that model that we created. Which I'm going to pick up. Now before running this, I already know that it's not going to work very well with some of these things. I think I got my labeling off slightly. So let's run this anyway and see what happens. So if I click run, it should open up a window. Let's wait for that to pop up. There we go. So if I hold up the, it also looks quite slow. So it's saying ESP32 camera. I know it's not, but the fact that it recognises that object amongst everything else that's in the background means that our model is working. That one said, was it French onion soup for a second, which I thought was quite funny. So let me get this into focus. Again, I know that's not a Raspberry Pi Pico or a car, but it is recognising that as something that's in the model. Now if we go back to the Uno, let's try that. Does it recognise that? So it's saying Arduino Uno on there. I think it only had one image to go off, which is it's like nowhere near enough images. And finally we had the Raspberry Pi Pico. So what I'm aiming for with this is if you point the camera at a whole bunch of microcontrollers, it'll be able to tell you exactly what they are, and even nuances between, what's the difference between a Pico and a Pico 2. I want it to be able to sort of, recognise that those two things are different, and it will be able to do that once we've trained it fully. So yeah, French onion soup here. And that's just because I've not trained it enough, as you've seen. So I'm just going to stop that now. It's going to freeze me for a second, I think. I'm just going to quit that, because sometimes when I do this, I've not frozen really. That's just the screen share that looks like that's frozen. There we go. Cool, let me jump back to my notes then. Cool. So I've got a question there from Nick. He says, do you have a train model on a Raspberry Pi AI camera, or could you use a train model on a standard Pi? What's the minimum requirement of a Pi? So you would probably use the standard model on a Raspberry Pi, and a Raspberry Pi 4 upwards is probably going to work okay. I've been working on machine learning models since about the Raspberry Pi 4. I think the Raspberry Pi 3, did that have like a gig of memory? And it also had like less cores, I think. I'm speaking off the cuff here, so I'm not sure, but Raspberry Pi 4 is more than good enough, I think, to do that. 5 even better, and if you've got the 5 with either the AI accelerator or the AI camera, if we can get these models quantized properly, they'll work very, very fast, like 30 frames a second fast. So yes, that's definitely worth looking at. And we have another question there. Let me just bring that one up. So I've decided to learn machine learning, and I doubt which language I should use, Python, or should I do DSA Python or other? Your help is appreciated. So I would use standard Python, and I would learn the libraries that are used with machine learning, like PyTorch, TensorFlow. I'll get familiar with that tooling, things like how you do image annotation. I could have done all this in VM, for example, and it would probably been a lot easier to do that. But I wanted to kind of show you the way of doing this using open source free software. Cool. So I'm just going to get back to here. Let me just grab that. So if you want to grab yourself one of these hats, I've got these for sale on the kezrobots.com/merch. You can get yourself a Robot Maker hat, available in different colours, and they are real conversation starters. If you're walking around an event hall, you've got one of these on, people will come up and talk to you about that, because they're like, talk to me about your robots. If you're not on our Discord server, you definitely want to jump on there. Head over to kezrobots.com/discord to get yourself a sign-up link. It just takes about 3 minutes once you've signed up to get the email confirming that. There's lots of people on our Discord server now, lots of conversations, people sharing projects and so on. And I'm also on, I'm also on social media, so if you want to find me on Threads, I'm Kevin McAleer at threads.net. I'm on TikTok at Kevin McAleer6. I'm on Instagram at Kevin McAleer. I'm on X at KevsMac. On Mastodon at kevsmac at mastodon.social. And on Blue Sky at kevsmac at bsky.social. And I post all kinds of behind the scenes things, so you can see kind of what I'm working on. And so on. Just realised I'm looking at my camera there, and I've not shown you what that looks like. I might do that in a second or two. So yeah, if you want to get your name in the end credits, then go over to kezrobots.com/coffee, and you can get your name in the credits there. You can also do the super thanks, super chat, join the YouTube membership program, or also the Buy Me a Coffee membership program too, if you want to help support the show. So let me give a shout out to the people who have done exactly that right now. So we have Stephen Gale, we've got Johnny Wilson and Marie-Louise Mayer, who have all bought coffees in the past month. Thank you so much for doing that. It's always a delight when I see that on social media and it pops up and says somebody's bought your coffee, and a little comment as well. I always love reading those. And we've got a couple of members on the Buy Me a Coffee. So we've got Andy Brooker, we've got Shemi, we've got Marie-Louise Mayer, Jeff Johnson, Steve Phillips, Dean Corty, Marlene Brent and Tom. And then on the YouTube membership side, we've got Bello, we've got Oxrad39, Littleback, Paul Cummins, we've got Johnny, we've got Hans from Cheerlight, Stephen, John Paul, Alistair, Cassie, Tinkering Rocks, Johnny, Michael, and we have Tom as well. So thank you so much for supporting the show. And if you want to get your name in the credits here as well, just hop over to kesrobots.com/credits to do just that. And yes, that tells me this is the part of the video where I'll say YouTube will be suggesting another video over here that it recommends that you watch. So definitely check that out. Let me know what you think. And yeah, happy coding on machine learning models. So at this point in the video, I'll say thank you so much for watching, and I shall see you next time.